let's just, so how many times do I have? So 5 minutes. So the idea here is that you have to cut this one loop specific amplitude into 4 maximum cuts, and its product of 4 tree amplitudes. And the reference spinner, of course, we can choose arbitrary as we want. So let's just consider 1 to be particle 2, and we can see 2 to be particle 1. The reference spinner. Here I will use identity here. P2 is a 0, is projection. This can be written as P1. So this the trace terms here can be written actually to be the 4 terms, but to be 3 terms, where you have the contraction is P2.L, P1.L. There's another P1.L here, and P1.L, so there's 2 terms here. And the other is a crossing contraction, the P2.P1, and there's the L squared. There will be an overall factor, which I don't pay attention. So, so what is P1.L here? This can be we can write this as P1 plus L squared minus L squared. So this basically gives you its difference of 2 propagators. This is L propagator, this is L plus P1. And we remember we have imposed this cut condition. So all internal propagators are on shell in D minus 2 dimension. So these the first terms have to be vanished. We can neglect about this. So what's the second term? And here it's a bit more subtle. You want to be really attention, because in this case, L is contracted with a particle with a spinner, which is exactly defined in 4 dimensions. L here is L4D. So we want to, so we know that L squared is equal to L4D squared minus distance squared. So this is replaced by mu squared. So basically this would be 2 to 1 plus mu squared. So if we do the similar computation for the other 2 terms, what we got is basically mu to the 4th power, and there will be 1, 2, 3, 4. Let's see other case contribution. So this is exactly what we want to compute. It's a Carl integrand. So if we lift this to the propagator, so there is actually an integrand, one integral, which is mu false as a numerator. So this integral we can integrate out. It's basically it's actually is 1/6 up to some size plus epsilon. So that's basically the how just by performing these 4 cards we can detect almost the final answer. This one loop QCD amplitudes by using very simple 4 cards. Of course, in this case, we need actually still need to check other cards. So the 4 cards is not all possible cars. You have to check double cars. There could be triangle in principle that cannot be detected by phone cars, but it doesn't happen here. So that's exactly the fine concept for QCD 1.
You say here the dependence on the higher column view just drops out.
Sorry?
Dependence on the column. We use higher column term?
Sorry, mu is defined by this condition. It's minus 2 epsilon components of your local momentum. It's
View B is a higher column. Is mu a higher column?
Well, in this calculation, mu effectively works like a higher column. Because the whole thing there is what the momentum goes before that. But there are other amplitudes, voicing amplitudes, namely the ones that are non-vanishing at theta. In that case, there are other terms that don't have mu's in the numerator. They're divergent.
yes, in some sense. I'm not sure, but the original term has a physical origin related to UV divergence. The original terms.
The rational terms are sort of like
Sorry for the. Thank you.
At the time of Hadron physics, there are many, many works on form factors. And I just went through some of the method and notions can be used in this context.
For the form factor program. Yeah, yes, exactly. So actually, although I focus on amplitudes, this analytical properties is actually universal. So this BCFW recursion relations, you can basically apply directly to the form factor picture up to some, for some operators, you need to worry about this, whether it has infinite poles, the pole at infinity. So that's potentially, but just based on this analytical properties, this is actually universal. It doesn't depend.
Are you concerned about the form factor in the small momentum or large momentum?
For the form factor.
But soft or hard form factors?
Actually, that's so it will be the particles. So what normally defined is with this the local operators in terms of momentum by Fourier transformation is Q. One can take arbitrary.
Is large or small? Or
Arbitrary.
or division?
Yeah.
perhaps you want using the conservative TCD as valid and both I's or reports and nuance. Because some people discuss form factors and sonic TCD where I's are they're you're not as interested in that.
I think it's a very interesting question for this lecture. Actually, I will tell you some very nice formula, like Pactel formulas, which already appear for the form factors. And then I will mostly focus on the form that actually you can study this spin analytic formalism for the full class of operators in the force examples. And this this general operators actually plays an important role in terms of the spin chain picture. And the analytic properties that we use to study those spin chains, in the relation to spin chains, actually you don't rely on integrability techniques because we use this analytical properties. So in principle, the picture that we study the form factor for the arbitrary operator applies to general case theory.
Can you write the dispersion relations for the form factor?
Sorry, please.
Can you rather than dispersion relation.
Dispersion relation. I think that's the icon that we talked about mentioned. It's a
When we speak of the full map, it equals 4 granules. Are you still working at origin or near the origin?
it's just an
I mean, they're extremely well defined, finally far away from the origin. And in that case, I suppose here, if you put in the direct parallel, we try to come to slightly going slightly away from the origin. We keep your momentum pretty much bigger than that of the scalar fields. But there's something you can say. I mean, form factor is supposed to be well defined for arbitrary closed step. But there's something else you can say with the opposite limit, which momentum is very low compared to the closed step. In that case, the spot is broken almost symmetrical. Some constraints are soft theorems involving field combination. But I wonder how would we interpret within that.
General, how do you detail renormalization?
Sorry?
Detail renormalization.
Renormalization.
Yeah. Let's say not the form.
I think at the technical level, this is the method is true for both UV and infrared divergence. Actually, for the renormalization, in particular, I think the operator that in the lecture, it's not necessary to be BPS operator. So in the form factor computation, even if it's false down mules, you will require to introduce renormalization for those operators.
We're saying that those things are to be discussed.
Yes, I will give you some examples that form factor contain UV divergence, and you need to do renormalization even in false
If we diagonalize it, you come up
No. The particular picture that we start from non-eigenstates actually. So, but then you can obtain this renormalization constant matrix. Then after that, you can diagonalize. Actually, this will be important. I think. For example, for false diagonals, the two-loop direction operator is not known. So that means the eigenstate is not known like two-loop operator. So, but in this way, you can at least compute the Hamiltonian, which allows you, if you know the Hamiltonian, allows you to diagonalize the eigenstate. But the final goal is because the eigenstate is the function.
So, are there any more questions?
So, is there a way to apply this to the massive state?
Sorry?
Is there a way to apply this to the massive state?
The massive states, yes. Yes. I think one complication is that the spin elasticity that is not applied directly to massive states. But I think after that, the picture here, for example, except that recursion relations, you can generalize to the massive particles as well. Also in entirety, I think this is the last example I showed. One example is that you need to generalize the on-shell momentum to the general B dimension. So this new parameter, in some sense, displays a mass for the 4 dimension. So it's not so efficient as the 4 dimension. For the massive particle quantity, it's general mass.
About the form factor equals 4, again. I have another complaint to make working at work, which is that normally with the form factor, you want to be able to say that suppose you get a 2-point function, it's a complete basis of being spatial out states. Sum over that state, you will
organic. So